Do you know Empedocles? Empedocles was a pre-Socratic philosopher who studied cosmogony. Cosmogony is the study of the origins of the cosmos. And Empedocles was the first known person to ask the simple question, what is light? He believed that Aphrodite had formed the human eye and lit a fire in it, allowing us to see. But if that were the case, then we would see just as well at night, so he hypothesized that the sun's rays could be linked to the rays that come out of our eyes. A fanciful idea, I know, but if it weren't for him, we might not have had the counter-theories of Aristotle, then Euclid, then Al-Haytham, Kepler, then René Descartes, Robert Hooke, and finally, Newton. In his book Opticks, first published in 1704, Isaac Newton experimentally demonstrated that white light was composed of a range of colors, and that colors are a property of light itself. This was a radical change from the vision of the past, and in today's video, we will analyze the experiments of Isaac Newton that changed the course of history and defined the world as we see it today. Analysis of Newton's experiments. Today, we will be looking at Book 1, Part 1 of Optics by Isaac Newton. Isaac Newton's first book of Optics has as its main goal to demonstrate that white light is composed of a combination of different colors, the visible spectrum, and that these colors are intrinsic properties of light itself, not external modifications or alterations. One of the goals of this book is to demonstrate that colors are not created by the interaction of white light with shadows or materials, but that colors are already present in light. This means that color is a fundamental property of light itself and does not depend on external conditions. Newton introduces the concept that the color spectrum is continuous, with no sudden jumps between colors, and that each color corresponds to a specific wavelength. This establishes the scientific basis for the modern understanding of the nature of light. The goal of the following theorems and experiments is to show that the colors of light differ in refringence, that is, the degree to which they are bent when they pass through a prism or other transparent material. When we say that colors are bent, we are referring to the physical phenomenon of refraction, which occurs when light passes through a transparent material, such as glass or water. The light changes direction as it enters or leaves this material, and it is this bend or change in trajectory that we call a bend. Proposition 1, Theorem 1. Lights differing in color also differ in degrees of refrangibility. Experiment 1. When a half-red, half-blue paper is viewed through a prism, the halves are separated. Blue light is the more refrangible. Experiment 2. A lens produces blue and red images at different distances. Description of the two experiments. Here's how it works in detail. Light travels at different speeds in different materials. When it passes from one medium to another, for example from air to glass, light slows down or speeds up depending on the properties of the material. This change in speed causes a change in the angle at which the light travels. In effect, the light bends or deflects from its original path. This is known as refraction. A prism is a triangular-shaped piece of glass that uses refraction to separate white light into its component colors. Each color of white light travels at a slightly different speed in the glass of the prism, so each color changes direction differently as it passes through the prism. When you look at the paper divided in half, red and blue, through a prism, the light reaching your eyes is bent, but this does not mean that one part of the paper physically covers the other or that the colors change proportions. The visual effect you see is due to the light of each color being refracted differently. Blue light is bent, refracted, more than red light. This deviation is visually manifested as an up or down shift of the two colors, depending on the orientation of the prism. It is not the paper that moves, nor do the red and blue portions change shape or coverage, but rather the light that, passing through the prism, arrives at your eyes from a different angle. What the paper looks like. The red part and the blue part no longer appear aligned. In practice, you'll see the blue part moved higher or lower depending on how the prism is oriented than the red part. Even though the paper is a fixed rectangle, the optical effect causes your brain to perceive the two parts as misaligned. The blue light, being deviated more, appears to come from a higher or lower position, while the red light remains closer to its original position. This happens because, as Newton demonstrated, the blue light has a shorter wavelength and is refracted more. Red light has a longer wavelength and is refracted less. As a result, when you look at the paper through the prism, the blue part appears more shifted than the red part. Proposition 2, Theorem 2. Sunlight consists of rays differently refrangible. Experiment 3. The text of the experiment is written as follows. A beam of sunlight is passed through a prism and an image or spectrum formed. Position of minimum deviation is used in this and following experiments. Detailed description of spectrum. Effect of changing beam size. Water-filled prism. Experimental results disagree with accepted laws of optics. Experiment description. Since the text is written in this manner, we will analyze each of the points that Newton divided from each other. Position of minimum deviation. In this experiment, Newton used the position of minimum deviation to ensure the most accurate results. Minimum deviation is the condition in which a ray of light passing through the prism is deviated as little as possible from its original path. This point is important because it provides the clearest and most defined spectrum, with the least distortion due to the angle of the prism. Detailed description of the spectrum. When sunlight is passed through the prism, it breaks down into a continuous spectrum of colors which Newton carefully describes. Red. This is the color that appears at the top of the spectrum and is deviated the least. Orange, yellow, green, blue, and indigo. These follow red in a continuous order. Violet. This is the color that appears at the end of the spectrum and is deviated the most compared to the other colors. Newton observed that each color has its own specific wavelength and that the spectrum is not divided into sharp bands, but rather is a continuous gradient where the colors blend into each other without interruptions. Effect of changing beam size. Newton also experimented with varying the size of the light beam that was passed through the prism. When the light beam was very narrow, the resulting spectrum was well defined, with sharp edges between colors. When the beam was wider, the spectrum was less clear, with colors tending to blend and overlap more, making the distinction between colors less clear. The experiment demonstrated that the size of the light source affects the sharpness of the spectrum. Prism filled with water. In another variation of the experiment, Newton used a prism filled with water instead of a glass one to study whether the material affected the phenomenon of refraction and dispersion of light. Although the angle of deflection of the light was different due to the different optical properties of water compared to glass, a spectrum of colors was still formed. This showed that the dispersion of light, i.e. its separation into the colors of the spectrum, does not depend on the specific material of the prism, but rather on the properties of the light itself. Experimental results disagree with accepted laws of optics. In Newton's time, traditional optical theories believed that white light was a sort of pure entity, and that colors were the result of a modification of white light caused by materials or by interaction with the environment. The results of Newton's experiments were at odds with these ideas because he showed that colors are an intrinsic property of white light. White light is actually a mixture of different colors, and the prism does not create colors, but separates them. Each color has its own refrangibility. Red light is deflected less, while violet light is deflected more. Conclusion. Through these experiments, Newton revolutionized the understanding of light, demonstrating that white light is not simple, but rather a mixture of different colors, each with a specific refrangibility. This refuted traditional optical theories and laid the foundation for modern physics of light. Experiment 4. Eye placed in various parts of spectrum. Light from clouds used. How the experiment works. In the fourth experiment, Newton used clouds to scatter sunlight. The clouds act as a large natural screen, allowing light to reach the prism and spread through it, without having a point source like a window, but a diffused light that fills the space. The crucial step in the experiment is to position the observer's eye in different parts of the light spectrum projected by the prism. By observing the spectrum from different angles or positions, the observer's eye perceives different colors depending on where it is positioned. If the eye is pointed toward the part of the spectrum where red light is strongest, it will see mostly red. If it moves toward the lower part of the spectrum, it will perceive blue or violet. This experiment demonstrates that light rays are not all deflected in the same way. Each color or ray is deflected at a different angle by the prism. The color red is deflected less and therefore visible in a position closer to the original light. The violet color is deflected more and is visible in a position further away from the original light. The fact that moving the eye to different positions allows you to perceive different colors confirms that the white light rays are differently refrangible. Each color of the spectrum has its own trajectory after passing through the prism, so it is possible to observe a specific color simply by changing the position of the observer. Observation in various parts of the spectrum allows Newton to experimentally confirm that sunlight is composed of different rays, each with a distinct refrangibility. Experiment 5. 2 crossed prisms used. Spectrum consists of overlapping circular images. Penumbra of spectrum is due to finite beam size and may be eliminated by use of lens. Separation of blue and red light originally incident at same place on prism. Experiment description. This experiment uses 2 crossed prisms to further explore the behavior of white light when refracted. The goal is to further our understanding of the different refraction of colors in the spectrum, such as blue and red, as well as how the use of lenses can improve the clarity of the spectrum. How the experiment works. Newton places 2 prisms so that white light passes through both of them. The prisms are crossed, meaning they are not aligned in the same direction, which means that the light is refracted twice, first in one prism and then in the other. This creates a more complex effect than if it were just one prism. After passing through the first prism, the light is broken down into the colors of the spectrum. But when it passes through the second prism, the refraction effect is intensified. The light is not simply separated into colors, but rather a series of overlapping circular images, each corresponding to a different color in the spectrum. These circular images overlap, creating a complex spectrum of colors with penumbras, out-of-focus areas, between them. The penumbra or fuzziness seen in the spectrum is due to the finite size of the beam of light entering the prism. In other words, if the beam of light is significantly wide, the colors of the spectrum tend to overlap and mix, creating a blurry effect. Newton notes that this penumbra can be eliminated by using lenses to focus the light beam before it enters the prism, creating a thinner, more precise beam of light, making the spectrum clearer and sharper. The experiment demonstrates even more convincingly that the colors of white light have different degrees of refrangibility. We are now at the end of this video. We will continue to analyze Newton's experiments on the nature of color and light in future videos. Follow us. This is only the beginning.